scientific process as a unifying thread to make connections in chemistry. In part 1, we discussed major activity 1, namely gaining empirical knowledge about nature using the tool of observing nature, the result being isolated facts. We also looked into major activity 2A, namely generalizing isolated facts and its first tool of comparing and contrasting isolated facts on some or other basis or set of bases, the result being empirical classifications. In part 2, we discussed the second tool of analyzing experimental data and looking for numerical pattern and recognizing the corresponding rule followed by nature in its behavior, the result being a law of nature. We also looked into major activity 2B, namely predicting one unknown property of a given system by doing calculation using the mathematical equation of a relevant law without doing any corresponding experiment. In part 3, we will look in detail into the first 4 tools out of the 8 tools of major activity 3 and the corresponding results. Isaac Asimov, a biochemistry professor and science fiction writer, said humans are curious animals. Given this trait of curiosity, scientific activity does not stop at the levels of major activities 1 and 2. If it did, science would be simply dull and uninteresting. We would be forced to just memorize millions of facts about nature's properties and behaviors. But the curiosity makes humans wonder why and how a set of facts, whether isolated or generalized, is the way it is and not some other way or in the opposite way. This in turn leads to the third major activity in the process of science, namely explaining already known facts, generalized and otherwise, as well as predicting yet unknown facts. In other words, we try to make sense of, understand, and hence explain the various facts of nature by asking the critical questions of why and how. For example, considering some of the facts we saw in parts 1 and 2, why do solids have fixed size and shape, while gases have neither? How does a solid change into the corresponding liquid state? How do temperature and pressure affect the physical state of a substance? Why do many elements follow the law of constant composition when they form compounds called Daltonides? Why do all chemical reactions obey the law of conservation of mass? In common parlance, to explain is to make something plain, clear, and comprehensible, as in he explained his plan to us. However, in science, the meaning of the special term explain with respect to major activity 3 is to logically provide a possible cause to answer answer the why question or a possible mechanism to answer the how question regarding a set of related facts, which is the effect of such a cause or mechanism. Initially, we attempt to use one fact to explain another. At one point, such an attempt fails since there is no other fact available to explain a given fact. It is in such a situation that major activity 3 comes into picture. The first tool is inductive logic in order to speculate on the invisible, unobservable aspects of nature and make certain specific assumptions about them after raising the question of how those invisible aspects could possibly be such that they bring about the effects called facts. The physicist and author of popular science books, Michio Kaku, states in his book Hyperspace, if all our common sense notions about the universe were correct, then science would have solved the secrets of the universe thousands of years ago. The purpose of science is to peel back the layer of the appearance of the objects to reveal their underlying nature. In fact, if appearance and essence were the same thing, there would be no need for science. Actually, no need for the third major activity 3 of the scientific process. Thus, peeling back the layer of the appearance of the objects in our imagination using inductive logic happens to be a tool that plays an important role in science. In science, each assumption made in major activity 3 is called a postulate. A postulate is a statement that is assumed to be true without our knowing if it is actually true or not. Yes, we have no clue at all as to its truth or otherwise. However, we put faith in it due to its ability to help us make sense of the facts that we know to be true. Postulates and facts form the two major parts of all scientific knowledge. While learning chemistry, it is important to realize correctly if each statement one comes across is a fact of nature or a postulate about nature, since it makes a big difference. The initial result of using the about tool of logical imagination about the invisible aspects of nature as opposed to a later result of using tool 4 in major activity 3 is a hypothesis, which is nothing but a collection of postulates. The sole goal of a hypothesis is making sense of, understanding, and hence explaining a set of related facts in the form of empirical classifications and laws, as well as those that still remain isolated and loose without being generalized. It is important to keep in mind that a hypothesis hypothesis is the result of human speculation, while a fact is the result of human observation. There exists a misconception that has been spread around by science fairs and hence taught by several teachers and professors. A requirement imposed on students by science fairs is to start their projects by stating a hypothesis at the very beginning itself. For example, when my 44-year-old daughter was in the 5th grade, she was asked to write a hypothesis that read something like, of the various cleaning agents available in the market, Tide is the best. At the very beginning of her report on her science fair project on cleaning agents, I was shocked. Hypothesis is often said to be an educated guess, and there is nothing educated about the above guess made just at the beginning itself. Instead, it is essential to do the relevant experiments and find out through proper observations which one happens to be the best cleaning agent. It is a fact that needs to be discovered through observation. It is not an idea to be invented using imagination. Speculation should play no role at all here at this stage. That is exactly the mistake the great thinker and philosopher Aristotle happened to make more than 2000 years ago. He imagined that when a heavier object such as a lead block and a lighter one such as a ping pong ball are held at the same height and then dropped at the same time, the heavier one would hit the ground well before the lighter one. That is, he thought that a heavier object would accelerate toward the ground to a greater extent. He could never think of actually doing it and observing what exactly happened. Nobody else did either, and everyone believed for nearly 2000 years in what he speculated on. He also said that the 4 elements that make up all matter are water, air, earth, and fire without ever making any corresponding observation. It was the motivating force behind the alchemists' attempts to turn cheap metals such as lead into gold. Aristotle's philosophy changed to modern science only after the following significant contributions. First, Galileo Galilei highlighted the significance of making observations at the beginning of the 17th century, including dropping of heavier and lighter objects at the same time from a given height and observing that they reach the ground at the same time. Then, Francis Bacon, known as the father of empiricism, advocated in 1620 that true knowledge comes from sensory experience and empirical evidence, that is, conducting experiments and gathering data. His ideas played a significant role during the scientific revolution, which marked a drastic change from the Greek era. And more importantly, in relation to chemistry, in 1661, Robert Boyle of Boyle's Law fame noted in his book titled The Skeptical Chemist, or Chemico-Physical Doubts and Paradoxes, that it was impossible to combine the four Greek elements to form any other form of matter, and it was equally impossible to extract these elements from any given form of matter. He therefore published his definition of elements. I mean by elements certain primitive and simple or perfectly unmingled bodies, which, not being made of any other bodies or of one another, or the ingredients of which all those called perfectly mixed bodies are immediately compounded, and into which they can be ultimately resolved by using appropriate separation methods. Thus, he suggested a practical, experimental method of identifying the elements in nature. Chemists then started to use various chemical methods, namely chemical reactions, and physical methods, namely methods that exploit the differences in physical properties of the components to separate the elements making up different forms of matter. Today, we are aware of more than 100 elements. As opposed to Aristotle's speculation, experiments have indicated that water, air, and earth are themselves made of elements. Fire or heat is understood to be not even matter thanks to statistical thermodynamic theory, but an agent or a mechanism we can use to change the amount of internal energy and entropy possessed by substances. From that time onward to this second, the starting point in science has always been making observations and gaining facts, as emphasized in part 1 of this video series as major activity 1. Speculation necessarily follows only later, with the sole goal of making sense of, understanding, and hence explaining those facts in terms of major activity 3 discussed here. The so-called educated guesses of facts made at the start of the science fair projects in the name of hypothesis only take us back to the era of Aristotle. It is completely wrong. Let us hope one day this practice will change. The first hypothesis to be framed in physics and chemistry was kinetic hypothesis, which was independently postulated by Daniel Bernoulli in 1738, John Hurapath in 1820, and James Waterston in 1845 to make sense of the behaviors of gases in terms of Boyle's law, published in 1662, and Charles's law, published by Gay-Lussac in 1802. They speculated on the invisible, unobservable aspects of gases, the easiest of the physical states to experiment with, and postulated the existence in nature of invisible teeny particles that constantly move around using kinetic energy. Hence, the name name of this hypothesis. The second in chemistry was atomic hypothesis framed by John Dalton in 1808 in order to make sense of and explain the existence of chemical classification of matter and the laws of constant composition and of conservation of mass discussed in detail in parts 1 and 2 of this video series respectively. He speculated on the invisible, unobservable aspects of elements and compounds and postulated the existence in nature of the particles called atoms that make up elements and compound atoms later referred to as molecules that make up compounds. In 1904, J.J. Thomson framed plum pudding hypothesis as a starting point for understanding the atomic structure. He imagined an atom to be a uniformly positively charged sphere on which negatively charged electrons are embedded like raisins on a pudding. Raisins were then referred to as plums. The second tool used in major activity 3 after framing a hypothesis is to imagine relevant thought experiments. Using the postulates of the hypothesis in question, the results of such experiments are predicted by using deductive logic. It is important to keep in mind the distinction between inductive logic used while framing a hypothesis and deductive logic used after framing the hypothesis. The inductive logic works by our raising the following question. If the facts are the way they are, how should the invisible aspects of nature causing them be? In contrast, the deductive logic works by our raising the following question. If the invisible aspects of nature are the way we assume, how should the resulting facts be in the context considered? If technology permits, the thought experiments are performed in order to verify the predictions. If the actual results agree with the predictions, our faith in the hypothesis gets strengthened and the process is repeated again and again. Otherwise, it gets refuted. For example, Ernest Rutherford thought of alpha scattering experiment and made predictions as to what should happen during the scattering of alpha particles by the atoms of a thin metal foil on the basis of Thomson's hypothesis. Hans Geiger and Ernest Marsden performed that experiment in 1908 and 1909 using gold thin foil which scattered alpha particles in various directions. If the actual results refute the hypothesis in question, the third tool used is to refine and modify one or more postulates if possible, or else the whole hypothesis is dumped and the speculation continues in a different direction, that is, to start anew with tool 1. The result is a modified old hypothesis or an entirely new hypothesis. In the scattering experiment, unexpected results were obtained which shocked Rutherford. backward. Specifically speaking, since Thomson assumed an atom to be a uniform positive sphere, Rutherford predicted the positively charged alpha particles to be uniformly repelled in all directions and hence continue to travel in a straight line, but a few of them were turned back almost by 180 degrees. In 1936, he recalled the following in an article titled "The Development of the Theory of Atomic Structure," published in Background to Modern Science, 10 Lectures at Cambridge. Then I remember 2 or 3 days later, Geiger coming to me in great excitement and saying, "We have been able to get some of the alpha particles coming backwards." It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that this scattering backward must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. It was then that I had the idea of an atom with a minute massive center carrying a positive charge. These could not be explained by Thomson's hypothesis. Rutherford realized that the plum pudding hypothesis could not be modified suitably but should be dumb. In order to make sense of the results, he framed his own planetary hypothesis in 1911 by postulating a nucleus at the center of the atom where the protons are packed together. The extranuclear electrons he imagined to revolve outside of the nucleus like the planet Earth revolving around the sun. If the hypothesis continues to elegantly explain known facts and successfully predict unknown facts at some arbitrary point of time, the fourth tool used is to elevate its status to what is called a theory. It is the same postulates that make up the theory, just the name changes from hypothesis to theory in the same way that the status of a given boy is elevated to that of a man or of a given girl to that of a lady. One should contrast the scientific use of the term theory with its use in common parlance. For example, the very next day after the recent unfortunate incident of collapse of the Francis Scott Key Bridge in Baltimore, Maryland, one could hear on the news that the NTSB chair and other members had a theory as to what could have happened to the ship that collided with the bridge. Here, it does not mean that particular theory was found to be very successful in explaining a number of facts. facts. The term is wrongly used as a synonym for hypothesis. On the contrary, in scientific parlance, a theory is always one that has been found to be very successful in helping us make sense of innumerable facts. It is a hypothesis that has been elevated in its status due to its extremely successful performance of its sole function of explaining facts properly and predicting them correctly. Similarly, in common parlance, one can often hear a statement such as, "It is just a theory," to mean it is just an assumption which we don't know if true or not. Although a scientific theory is also a collection of postulates or assumptions, the name theory is supposed to imply, as mentioned above, that those assumptions have been extremely successful in helping us make sense of facts, and we don't yet have any alternative to help us understand those facts. So, a science student can never ever ignore it by saying it is just a theory. It is very important for every student to understand a given theory always, since he or she is expected to properly and successfully apply it to explain relevant facts. James Joule, Rudolf Clausius, James Maxwell, and Ludwig Boltzmann developed kinetic hypothesis further, and two theories resulted from it. Kinetic theory of ideal gas resulted first in order to explain Boyle's law and Charles's law obeyed by gases under low enough pressures and high enough temperatures, and in addition Avogadro's principle that resulted from Avogadro's theory, as well as their mathematical combination called ideal gas law. However, normally this theory is referred to in textbooks as kinetic theory of gases, where the postulates of kinetic theory of ideal gas are generally wrongly included. Specifically speaking, it is said that there is no attractive or repulsive force between the particles of a gas. This is the assumption made only for ideal gas, not for any real gas, in which case weak attractive force is believed to exist between the particles. Also, it is said the collision of the particles is elastic, meaning no energy is exchanged during such a collision. This is also an assumption applicable only to ideal gas and not to any real gas, where the collisions are thought to be inelastic. The ideal gas is defined as a gas that obeys Boyle's law at all temperatures and pressures. Such a gas does not exist in nature. The above, as well as certain other assumptions, were made for ideal gas in order to avoid possible complications in the mathematical derivation of the ideal gas law from the postulates, and they are not applicable to any real gas. The second theory that arose was kinetic theory of matter, applicable to all three states of matter. It was the result of suitably modifying certain postulates of kinetic theory of ideal gas and generalizing the last postulate regarding translational motion to rotational and vibrational motions also to include solids and liquids. General chemistry textbooks don't even refer to this theory, although somewhere in the beginning of the textbook they use the idea of particles making up matter to distinguish among the three states of matter. It is always important to indicate the name of the theory that postulates the ideas invoked to explain the given facts. Atomic hypothesis was elevated to atomic theory and Rutherford's hypothesis to simple theory of atomic structure. The above theories, as well as thermodynamic theory, quantum theory, theories of chemical bonding, transition state theory, reaction mechanism theory, etc., are all considered today as extremely powerful theories, meaning they help us make sense of a whole slew of facts. For example, the immense power of kinetic theory of matter becomes very evident in the quote by the Nobel laureate Richard Feynman, who so elegantly raised the question: if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? And answered it using the following one sentence: little particles that move about in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. His reference was obviously to kinetic theory of matter, and he realized its enormous power. For the postulates of kinetic theory of matter and some of its explanations, see part 1A of my video series titled "The Most Important but the Most Incompletely Understood Concept in All of Science," the reference being to entropy. For the postulates of kinetic theory of ideal gas and the derivation of the ideal gas law equation, see my book Understanding Chemistry. The postulates of Dalton's atomic theory are listed here. We will make use of these postulates when we discuss the fifth tool of major activity 3 of the scientific process in part 4 of this video series. So pay close attention to these. The other examples of theory in chemistry are listed here. Including the theories mentioned earlier, it is clear that chemistry abounds in theories. As we will see in part 4, this abundance is responsible for making chemistry a very fascinating branch of science. In the absence of these theories, this subject, with its millions of facts, generalized or otherwise, would be, as mentioned at the beginning, a very dull subject. We would have to just memorize all those facts without understanding their causes or mechanisms at all. Each theory with its just handful of postulates connects together a very large number of otherwise unconnected facts. Hence, the significance and the power of major activity 3. Textbooks generally list the postulates of only less than a handful of theories. One may normally find the postulates of atomic theory and kinetic theory of gases in general chemistry textbooks and of quantum theory in physical chemistry textbooks. But for the postulates of each of the above theories, see my book, Understanding Chemistry. In part 4 of this video series, we will discuss in detail the remaining 4 tools of major activity 3 of the scientific process. We will especially look at the explanations offered by Dalton's atomic theory for the laws of constant composition of Daltonides and of conservation of mass discussed in detail in part 2.